This video summarises the reaction mechanisms in the AS OCR course. Now in your total course you're going to have 5 reaction mechanisms. The 3 that are appropriate for AS is free radical substitution, which is we use that for the reactions of alkanes. And we also use it with as an extension of halogen alkanes. Then we've got electrophilic addition, which we do with alkenes. So you're looking for the double bond in that. And then we've also got nucleophilic substitution, which is with halogeno alkanes. The other 2 mechanisms that you'll do in A2 are electrophilic substitution and nucleophilic addition, but those we will do next year. And just for just to sort of make the point, electrophilic substitution we do with benzene rings, and nucleophilic addition we do to carbonyl groups, C double bond O. So if we look at free radical substitution first, there are always 3 stages in free radical substitution. What a free radical is it's anything that with an unpaired, any chemical species with an unpaired electron. So for example, what happens with our first stage in free radical substitution is in the upper atmosphere, if chlorine gas, for example, ends up in the upper atmosphere, what happens is the chlorine molecule, which is 2 chlorine atoms bonded covalently, will absorb UV light and the bond will break, and it will break what we call homolytically. Now homo means same and lysis or lytic means to split, so we use curly arrows to represent the movement of electrons, and these are single-headed arrows to show that 1 electron has moved in each case from this bond but onto each chlorine, and so what you end up with is 2 Cl, and we represent a free radical with a dot. So we've generated 2 chlorine free radicals, and we call this our initiation step, and it's the first step with only 1 thing in it. The second step we call propagation. It's step number 2, and that's useful. In fact, remember it's step number 2 because that means it's got 2 reactions. Okay, so what we now use is we use this free radical, the chlorine, and we react it with whatever alkane we've been tasked with, right? So for example, if we do methane, what will then happen, the whole purpose of the propagation step is this first one, I've got a free radical, I'm going to react it with this, and I need to make another different free radical. So the chlorine will react with this, and I will make HCl and CH3, so a methyl free radical. I now use this new free radical that I've made in the next equation. So I'm going to react that methyl free radical with chlorine, and this will always, in this second stage, generate the first free radical that we started off with, and one other stable chemical, so it'll be CH3Cl, so methyl, chloromethane. We've made a halogenoalkane, which is important as part of our reaction synthesis, and then we get on to stage 3, which is termination. And remember, the fact that it's 3 is important because there's 3 equations. All I do is basically add together my free radicals. So I can take my 2 chlorine free radicals and I can make chlorine again. So I can do step number 1 backwards. I can take my 2 methyl, I can take any 2 methyl free radicals, and they can react together to give me ethane. And I can also do a combination, so I can do, which we've done already, I can take my methyl and I can take my chlorine free radical, and I can simply add them together to make chloromethane. So that's free radical substitution. So 3 stages: initiation, propagation, termination. 1 step in initiation, 2 in propagation. You must generate a new different free radical and then regenerate the next one. There must be free radicals on both sides because it's continuing the process, whereas initiation must make a free radical. And then the last step, termination, is adding your free radicals together. Now, just as a point with this, you could be asked to do this with chlorine, you could be asked to do this with bromine, but generally speaking, in actual alkene section, that's it. They can then vary the alkene, obviously, and it just, whatever the chain is, you just write it there exactly the same. So the next mechanism is electrophilic addition. So electrophilic addition we do with alkenes. So if we imagine we've got a double bond here on ethene, as an example. Not the most neatly drawn diagram, I apologise. But we've got this double bond here, and what we have is we have an electrophile. Now, an electrophile is electro, meaning like an electron, so negative, and phile means lover. So something that loves negative. So, for example, if I've got a bromine atom that approaches this double bond, because the double bond has a region of high electron density because of the pi bond that is over this double bond, what happens is that region of electrons will polarize this bond. So what we end up with is, as this molecule approaches it, this bromine ends up with a delta plus and this ends up with a delta minus, until we reach a stage where what will happen is the electrons in the pi bond will attach themselves to the bromine, and this bond will break heterolytically, hetero meaning different because one is receiving 2 electrons and one is receiving none, and we'll break this bond heterolytically. And so what we will end up with as our second stage is we will have our first carbon atom with bromine attached, and our other carbon atom will have quite literally just a positive charge, and I'll put my hydrogens in, and that positive charge will obviously then attract my bromine atom, which now has a pair of electrons in it. So you draw this coming from the negative, so it goes to the positive carbocation, and we'll attach for that, and then you will end up finally with dibromo ethane. Put my hydrogens in. So that's electrophilic addition, because you're adding across this double bond. You're quite simply just adding the bromine to this molecule. You could be asked to do this with HCl or HBr, which is slightly different because obviously this is a polar bond all of the time, because the chlorine and bromine is more electronegative than the hydrogen. So this is the positive and this is the negative. Whereas when you have a symmetrical molecule like bromine or like chlorine, then it's the induced dipole that then causes this process to happen. And this would obviously cause, again, a slightly different type of addition, because you're going to get a hydrogen on one point and chlorine on the other, which in this case, because it's ethene, doesn't only produces one isomer, but if it was, say, propene, for example, I could end up with a chlorine molecule attached either on the 1 position. So if I do a skeletal formula, I could end up with a chlorine there, or I could end up with a chlorine in the second position, if, for example, I reacted it with hydrogen chloride. So I can get a Racik mixture formed, which is when I've got a combination of stereoisomers. The last one is nucleophilic substitution, and so this is for halogenoalkanes. So you're looking for any carbon halogen bond, and the word nucleophile means nucleus, which is obviously positive, so positive, phile meaning lover, so it's something that it's a negative species that likes positive charge effectively. So if we take a really simple example, the chloromethane, because chlorine is more electronegative than carbon, this is a delta plus and this is a delta minus, just because of the electronegativity. So what will happen is if I take a nucleophile, it could be any nucleophile, but if we use OH minus as the example, right, the electrons from the OH minus will come from the negative and will attack at the back of the carbon, and then because of the positive charge, positive dipole rather, this bond will, just like in the electrophilic addition reaction, will break heterolytically because both electrons move on to this atom, and then what you will end up with is your OH group attached, and we call this reaction hydrolysis, and then you will end up with the molecule effectively inverted if we do it in 3D. Now you don't need to be able to do this in 3D, but it's nice to understand it in that way. And then we obviously get our chlorine. So if this was water, for example, I'd then make HCl as well. So this is nucleophilic substitution. So you need to draw the dipoles and draw the curly arrows from the negative charge, from the negative coming into the back of the carbon, and then from the bond onto the chlorine. The way I've drawn this isn't particularly neat. The dipole really should be in the corner, so that should come more to here. My apologies for that. The thing that affects the rate of the reaction for, say, the hydrolysis of halogen alkanes is you could argue that it's two things. It's either the bond enthalpy of the halogen alkanes, so or their polarizing ability, due to the difference in electronegativity. So if we compare the group, what we tend to see is that because fluorine is the most polarizing, we could predict that this actually has the biggest dipole, and so we could think, well, that's going to be that's going to increase the rate of reaction more as we go up the group. But fluorine is also got the highest bond enthalpy, and we find that actually it's the bond enthalpy that limits the rate of the reaction in this case. So the most reactive of the halogen alkanes via this mechanism is actually iodo compounds, because the bond enthalpy is weakest, and so it's easier for this reaction to happen, for this bond to break as a result of the substitution. It happens the slowest with fluorine, and we demonstrate this by looking at the formation of the precipitate. So we dissolve the halogen alkane in ethanol, and then we add silver nitrate solution to the mixture as it's undergoing this hydrolysis. The ethanol produces OH minus ions in order to undergo the substitution, and then the chlorine will attach itself in this case to the silver, and so you'll end up with silver chloride, which is a white precipitate, but that reaction happens a lot slower than the formation of silver iodide, which is yellow, which we see very, very quickly because of the bond enthalpy being the weakest. If you don't understand any of these reaction mechanisms, it's very important that you take the time to look at them, study them, look at the different examples, and are clear on them. Ask your teachers if you need to go over them again, but it is imperative that going into your exam you understand each of these mechanisms.